This video is going to be for anyone interested in joining me in imaging Artemis II during its flight. This presentation is going to be fairly rough. I'm not going to edit it, so bear with me, but we'll get through some interesting information. All right, so a little bit of background about Artemis II, the mission. So it will be the first crewed test flight to the moon since Apollo. There'll be 4 crew members on board. You can see them over here: Christina, Victor, Reed, and Jeremy. It will launch from Kennedy Space Center in Florida. It'll go around the Earth once, and then halfway around it will perform a apogee raise burn, and this will put it into a very high Earth orbit and a very elliptical orbit. And along that path, the first thing they'll do is do this proximity operations test. And so this is basically testing out the maneuverability of the spacecraft and getting ready to do dockings in the future. And then along the rest of this path, they'll do checkouts of the system. Then it'll swing by Earth. And Orion, and during this phase here, it'll separate from the upper stage, and that's what it's going to practice to on the docking sequence. And then when it comes back around the Earth, when it gets close to the Earth here, Orion will perform the TLI, the translunar injection, and that'll put it on its long course towards the moon. Then around the moon, this will be on a free return trajectory, so it'll make its maximum just beyond the moon, and then the moon's gravity will help push it back towards Earth, and then land in the Pacific Ocean off the coast of California. So this mission has a couple of interesting things, and one unique thing is this highly elliptical orbit that's going around the Earth at the beginning. And so this will allow for more ground imaging options, because once Orion gets on its way to the moon, it gets too small to image from Earth. So, and there's also because of this one time around, there's really limited chances to take this photo, and it'll depend on where you are on the Earth and when it launches. So it'll depend if you're in day or night, the weather, equipment problems, and challenges. So the more people that do this, the better chance that we'll all be able to get a couple photos of Orion during this flight. So that's why I'm making this video. All right, a little bit more about the launch opportunity. So as I mentioned, it's going to launch from pad 39B at the Kennedy Space Center in Florida. It'll be via the Space Launch System, or SLS. And the launch opportunities are roughly kind of in 1 week spans near the start of each month. Sometimes they bleed over to the ends of the month. So you can see here's the schedule on the side. The next opportunity windows is between the 1st and the 6th of April. And if something doesn't work out there, then the next one starts at the end of April, the beginning of May, for another few days. And each of these days, the launch window within the day is about 2 hours long. You can see some of the times listed below. And so the ground imaging really depends on what day it launches, where you are on Earth, and the exact time within that 2 hour window, because that can make quite a big difference on if different locations are in darkness or not. So you can see the rocket here at the pad. The SLS and the Orion sits on top here, with the launch abort system being at the very top, which gets jettisoned after ascent, or at the end of ascent. All right, so how are we going to do this? Well, the first thing is that during the Artemis II flight, the Flight Dynamics Officer, or FIDO, in Mission Control will release daily updates of Orion's trajectory and their planned trajectory for the whole mission. So this initial file will be posted a couple hours after launch, and that's what we need to be able to do the calculation to figure out where we can take pictures of the spacecraft from Earth. And the files will be in a CCSDS orbit ephemeris message format, which is a plain ASCII text file, has an extension .asc, and it lists the J2000 positions and velocity. So it's just basically a really long list of a time, an XYZ, and then the speed and XYZ positions, or the velocities in total. All right, so from that, because of this dynamic when it launches and the time it launches, I wrote a script to help automate looking for possible imaging opportunities. And I wrote it in Python. So first it reads the file, and then given some ground location as well as telescope and camera details, it looks for opportunities for imaging. So a couple things it actually outputs. It outputs the lists of opportunities from the ground via command text output and some plots to help you look at what times may be best. Then it also outputs a file that can be imported into an application called Celestia, and this really helps visualize the orbit in 3D, so you can see and kind of double check where the spacecraft is relative to the Earth, how the Earth is spinning around, and then where the Moon is as well. That's optional. And it also outputs a file and a script that can be imported into Stellarium, which is an open source planetarium software, and this can be used to visualize what your sky looks like every night and at any particular time. And this will then, using this file and script, you can actually show where the spacecraft will be at any point in time, and so you can plan your imaging session. All right, so we'll get on to how it does it. So the script that I've written really considers four main things. Then that's what I came up with that would, if I felt like if these four things were met, then you should be able to possibly image the Orion spacecraft from the ground. So the first one is it must have a large enough angular size in the sky, which basically equates to how many pixels or how many subpixels on a camera or the spacecraft would take up given a telescope and camera setup. If it's too small, it just won't be picked up by our cameras. It also must be above the local horizon, so we're on Earth, we're stuck on Earth. Sometimes, and Earth is spinning around, so sometimes it's just not looking towards the direction of the spacecraft. So by default, I put it as it has to be above 15 degrees above the horizon. That way, if it's too low, there's a lot of trees or houses or other things or buildings in the way. That can be changed. Also, the spacecraft itself must be sunlit, so it needs to be reflecting light. There is usually at least one point during the mission where it gets behind the Earth's shadow, and so in that case it wouldn't be able to be imaged. And then also the observer, or so wherever you are on Earth, you must be in darkness. And I picked astronomical twilight as the cutoff for darkness, both in the evening and the morning of when it's possible to image. So if all those are met, then there is a chance that you should be able to image the Orion spacecraft during this mission. All right, so let's look at just some example results, just so you can kind of see what it does. So given some test data, say a launch on April Fools, on the 1st of April, and giving a ground location of League City, Texas, and then a telescope. This is the telescope I usually use. It's an 8-inch Schmidt-Cassegrain, and then a 0.7 reducer, just for this example, and then a camera with 3.76 micrometer pixel size. So with that, I ran the script. At the beginning, it just spits out a bunch of kind of what the constraints are and some intermediate calculations. It just shows like how many data points are in the data file, and then at the very end is the most important one. There's also a bunch of other stuff it spits out along the way, so you can look at all of the individual constraints. But the bottom one is probably the most important, and it basically looks for when all of those conditions are met. And in this case, there's only one feasible time period, and it starts on April 2nd at 1:39 in the morning, local time. And this will pick up your local time based on whatever computer you're running the script from. And then it'll end on the 2nd at 5:15 a.m. local time. All right, so we'll dig into that just a little bit better, but this will give us a good heads up on when we can start planning to do imaging. And this may not, so if it really launched the evening of the 1st, there isn't a lot of time in some cases to get this imaging, and so the file will have to be, the updated trajectory file will have to be getting quickly, and then you'll have to run the script and then be prepared to image in a fairly short order, depending on where you are and depending on where Orion is in that the orbits. You may have 6 to 12 hours possibly, or longer, but you also may have a short amount of time. So in this case, it's really short for this location. Okay, the plots that it spits out looks like this. Also, just note that you can use this zoom function, and this interactively zooms all the plots at once. So if you zoom in for some time sequence on one of the plots, it'll automatically zoom in on all three. The top plot itself, and this is specifically for this location, is the angular size across the entire mission. So across the horizontal axis is what I'm just calling a mission elapsed time. And this is mission elapsed time from the start of the file. Typically that usually means mission elapsed time from launch, but in this case the data set picks up when the upper stage separates from Orion. And so we're going to call that 0 just to make this a little bit easier. All right, so that is on the horizontal axis, and then what's plotted on the vertical axis for this top one is the angular size. So this is the arc second size. And then I've drawn a red line where the minimum sized image, which is 0.1 pixels, and whatever that comes out to be is on there. So you have to kind of zoom in to really get to understand if it's above or below that threshold. And this peak here is where Orion comes back around and gets really close to Earth before it does the burn, the translunar injection burn. And it gets quite big in the sky because it's much closer. All right, the second plot just shows the altitude in degrees above your local horizon. So anything above 0 is above the horizon. And I've also drawn the red line to represent that minimum altitude of 15 degrees. So anything above this line means this Orion spacecraft would be above your local horizon, and you should be able to see it in the sky. And then all the other times are it's below the horizon, or it's kind of hidden behind the Earth. And then the last plot is about sunlight. So I've just combined both the Orion spacecraft, which is shown in blue, as well as your location in green. And for the Orion spacecraft itself, when it's at 0, it means it's in shadow. So you can see this one point in time here when it goes behind the Earth's shadow. And when it's at 1, that means it's in sunlight, which is most of the mission. And then the green is the ground site. So when it's at 2 here, that just means the ground is in shadow. And the top line means the ground site is during the day. So from the top, you need the values to be above that red line. From the center one, for the altitude, it needs to be above the red line, above the horizon. And down here, you need the spacecraft to be lit, so the blue needs to be at 1. And your ground site needs to be in dark, so it needs to be at this bottom, or the 2 value across the bottom. So I'm going to zoom in just a little bit more into kind of the time period that recommended by the script. So and also I've just highlighted it green. This is the time where it said it was feasible to image. So looking at this, you can see this plot is hard to see, but it must be slightly above in angular size. The second part is where it comes above the horizon, but it stops here before it actually sets. And the reason is, if we look down at the bottom plot, we can see Orion is lit, but towards this back side here is where the sun rises and it becomes daylight, so imaging is no longer possible. So that's the kind of the constraints. That's the best chance to image Artemis II for that launch time and day and that location, and given the telescope setup. So just looking around the plot, there's this interesting thing is, man, it would really be nice to image Orion here because it's really big. And it looks like it's above the horizon for part of it. So man, this looks really nice. But the problem is, looking down here, it's during the day for this site. And also Orion does go in shadow for part of it too. So kind of has 2 strikes against it down here. But anyways, that's why I thought it would be interesting if more people wanted to join in on this, because especially if people are distributed around the world and have different weather and have different locations, we'll be able to have different opportunities to get some pictures. All right, so then you can also visualize where in the sky, and I think this is probably the best feature of this, and so you can really relate it to your local sky that evening for doing planning. So this is just right out of the script at the beginning. There's a bunch of comments to help how to use the files that are output in Stellarium. I'll just quickly go over this, but here it's a reference, and it's also when you download it, it's listed there. But the main thing is that you need to copy 3 files, which are 2 .inc files and then 1 SSC file. And you need to copy them into the scripts folder for the Stellarium application. And it depends if you're on Mac OS or Windows. If you're in Mac OS, you have to go to the application file, which is either in applications. I have put it under an astronomy folder, so that's a custom. Yours might not be here. You have to right click on this app for Mac OS and say show package contents, and then you can navigate to content, resources, and scripts, and you just copy these 3 files into that location. And if you're on Windows and it's in C program files, Stellarium scripts, just copy those 3 files right into there. And then once you're in Stellarium, the main point is to make sure your location in the software matches your location. Then you can just change to the current time or during the Artemis II mission. Otherwise, the spacecraft won't show up. And then you can kind of change. Then you have to start the script that's given, and then you can change times and see where the spacecraft moves. And I'm going to do a little demo of that. I have a pre-canned video. The rest of this comments just kind of help show some of the, if you haven't used Stellarium before, some of the keys and some of the buttons you need to push to kind of change time and kind of navigate the software. All right, so here is Stellarium. And I'm going to play the video here. So I just have a custom landscape, so it kind of looks, I can see where things are blocked from my driveway. So I'm going to set the day to the proper day. So we'll go on April 2nd. We'll pick some time that's in kind of that time span that was predicted by the script. So we'll put it at a little after 2 in the morning. And then once that's ready, we have to go run the script. So this is assuming we already copied those files over. And then so you open up this configuration panel, then you hit the scripts tab, and then you look down the list until you find one that's called Orion, Artemis II, Stellarium. So you click on that, and then you need to hit run or the play. So you play, and then the script will just continuously run in the background, and what it's doing is updating that position of the marker that says Artemis II. So it isn't static in the sky. It will be moving around, and there's maneuvers. So that's why it can't be a standard item in Stellarium. And then, so here you can just change your things like how you can look at what your sensor and your telescope would see, the field of view. And then you can change the times, and you can see how the spacecraft moves around in your sky. And you'll notice here, so here, I think I forgot to specifically fix the camera, so it does jump around a little bit, but the next point I will fix it better on a star. So I'll pick a local star, center it on it, and keep it centered. So this will be like tracking mode. And then you can see even over the course of a few minutes, Artemis II will transverse your imaging field of view. So if you take a long exposure, you should be able to get a streak that is Artemis II across that image. But using Stellarium, you should be able to pick out a few points in time and a few locations to aim at to try to image the spacecraft during the mission. And then if you click on the name itself, you can get the information like the right ascension declination or the altitude and azimuth. The rest of the data like rise, set, that might not be accurate depending on if there's a maneuver in between those times. But all right, so I think that's pretty helpful. on being able to plan the session using Stellarium. You can also, the other optional thing is to view the mission in 3D, and using an application called Celestia that you can download. And the main thing here, you got to do a couple different things. The script will generate two files, one .ssc and then one xyzv, which is the data. You have to copy that to Celestia's resource data directory. And here's are the two paths for macOS, which is a very similar thing. You have to go to the application itself, right click on it, and then say show contents, and then go to contents, resources, Celestia resources, data, copy them into there. For Windows, it's much easier. C program Celestia data, and then copy the files to that location. But there's one extra thing you have to do for Celestia is you have to edit this config file. And you have to find this, there's a section that has the solar system catalogs. And at the very end, you just have to add an extra item. You should see the example of a whole bunch of other things in there. Just add it to the bottom of the list. Add, in quotes, the data / Orion _ Artemis _ 2 _ Celestia.ssc. And then make sure it's just within that last closed bracket. That will define a big list of all the items that it needs to load. In macOS, you can find that config file under this path or something similar to it. It might not be in the astronomy. I added that specifically, and here it is on Windows. Then close down the application, restart it, and you should be able to get it to work. The rest of this information is how to pause time, which is the space bar. It pauses and restarts it. You can control time by using L to go faster, K to go slower, and J to invert the time so you can go forwards and backwards. And then the other thing is you have to select and center on Orion. It makes it much easier to follow along. So I'll be showing that here in the demo real quick. But here, again, in the script comments at the very top, it lists all of this information. You can kind of read through it to help if you haven't used this application before. Okay, so here's the quick demo of that. So once it loads, it usually centers on Earth. The first thing we need to do is set a time, and we need to pick a time that's sometime during the mission. So I'm going to do April 1st in this case. And then I'm picking a time that is sometime within the data set. So I'm going pretty late in the day. All right, so then hit set time, and then if you then navigate, you can use your mouse controls to spin things around, zoom in and out, as well as pan. But at the top, make sure you go to display and then labels, and make sure spacecraft and moon are on. Go to orbits, make sure moon and spacecraft are on. On Windows, it's a little bit different. It's in a different location, but I highlight that in the notes in the comments. And then the last thing is you want to go to the browser, so location browser, then hit planets, and then Earth, because we need to drill down to where we are, and then look under spacecraft, and then Orion should show up if you've copied the files in the right spot and added that config file. Then hit follow and center, and then go, and then you can get rid of the browser and it'll zoom in on the Orion, which I didn't put a model there. I just have a nice white sphere. But then you can zoom back out, and then you can spin things around to see where Orion is. You can see where it is relative to the Earth, which is pretty cool. You can then, if you look at the Earth itself, you can see where the continents are and which parts are facing the sun. This helps visualize kind of those results. And then if you hit L to increase the speed of the time, then you can see Orion makes that one pass around the Earth, and it makes its way out to the moon. So if you slow down when it gets closer to the Earth, you can see those times when its imaging is possible. Here, just for the fun of it, I'm going to go show the whole mission where it goes out. You can see the moon. So Orion is aiming out ahead of the moon, so it'll be where the moon will be when the moon gets there. It's kind of like aiming ahead. And then once it gets past the moon and the moon's gravity interacts with it a bit, it helps slingshot Orion back around. And then you can see how it's going slower out here. And then it heads back to Earth. As it gets closer to Earth, it gets closer, faster and faster. So this is due to Kepler's laws, equal area and equal times. Lots of fun orbital mechanics going on here. But that's the demo. So if you are interested, you could play with this and see the geometry of the mission using this tool. All right, so just to set expectations about what it will probably look like is it'll probably be either a dot or a streak of light in whatever image we're able to capture. So you can think of it basically as, hey, as astrophotographers, we try to really avoid satellite trails, or we don't really like them when they show up in our images, but that's what we're trying to do this time. So instead of avoiding them, we're trying to create one of those streaks in our image, and then we can say, man, there's people on board that spacecraft that are headed to the moon as part of that mission. I think that's pretty cool, and it should be really interesting to get some photos. Hopefully it works out. And then at some point we got to figure out how to share these images. So as people take them, especially if those of us, I suspect with my luck I'll get bad weather, but it would be really awesome to see at least some photos of this. So we'll have to come up with a way to share it with each other. Here are just some risks or some things that could prevent this from working, as well as some trade-offs that you can think about when you're imaging. The first is there could be a delay in releasing that trajectory file. So hopefully that isn't the case. Hopefully it's early enough that we can get it in time and predict some possible opportunities to image. I'll be right on top of that for when it comes out and show you some places that you can check for when that will be released. Obviously weather for each location. Also, there could be some miscalculations on my script or in the trajectory file itself. So there's lots of things going on: time conversions, unit conversions, coordinate transformations. It's all open source, so feel free to double check, and I would actually appreciate it if someone did. Also, Orion's maneuvers could be slightly different than the published trajectory as it goes. As this is real life, things don't go exactly always as planned, but hopefully they're really close. Orion's orientation may also be such that it doesn't reflect much light back to Earth. There are thermal constraints on the spacecraft, so they're trying to minimize how much light is built up on the surface itself to reduce the heat load on the spacecraft. So we just have to watch out for that. So that will be kind of impact how bright it is when we're imaging it, and where the sun is relative to the spacecraft and the Earth at the time. So there's also some trades or decisions. Should you use more of a wide field view or some long focal lengths and really zoom in? The wide field ones are nice because they're more tolerant of errors. So in case the timing is slightly off or the trajectory is slightly off one way or the other, this wide field will be able to capture that somewhere in the view. But it's also then more dim. It's dimmer in that view because you're taking a bigger, broader area. If you're zoomed in, you might be able to see it better, but then you may miss it if there is some errors in some of the calculations. Some other ideas are: do you leave tracking on? Do you just set up a camera, possibly on a tripod, and try to get the stars to trail and Orion to trail in a different direction? So there's kind of different ideas there, and then hopefully people can try different combinations of these to see which one works best. All right, so what do you need to do to get ready? So these are some first steps you can do now. The first thing is to download and install these different applications. The first one is Python itself. This is what's needed to run the script. So you can get that from python.org. Just install one of the latest versions. We also do have to install some additional libraries, but those will come, that detail will come later, and that's after you've already installed Python. And then to make running the script easier, it's pretty easy to use like an integrated development environment or an editor. I recommend for this Visual Studio Code, so it's available for Mac and Windows. And then you have to enable the Python extension, which I'll show you how to do that here in a bit. install Stellarium, which you can get from stellarium.org. Make sure you get the desktop version. There is a web version. That won't work in this case. And then install Celestia if you want to view that 3D visualization. And then finally download the script that I've written with some test data, the test data that I've shown here, that you can test it against your location. So you can get that from www.gno.name/Sean/Artemis II. And so you just have to, I'll show you what it kind of looks like. It's a really small website, but just mainly there to host the script and give updates on when the trajectory data is released. So inside of the script, we'll have to customize a couple things to set up for your location and your telescope setup. And then later during the mission, you'll have to download the updated trajectory, and then make sure you change the whatever that file name is, put it in the same location as the script, and then change the name of the trajectory file in the script. And I'll kind of show you how to do that in a bit, but that's important to do. All right, so this is just a quick screenshot of the web page given above. So the first thing you need to do is download where it says Python script right here. Just click that and download it. It'll be a zip file, and you have to unzip it on somewhere on your computer. On Mac, I think you just double click, and Windows, I think you can right click and say uncompress here, and it'll uncompress into a folder. Then you can move it somewhere wherever you want on your computer. And then I'll update this where it says link will be here during mission. They may provide some predicted trajectories even before the mission, and they'll probably just pick either the open of the launch window or the close. So it probably won't be the right time, but at least it'll be some other data to try out with once it's here. And then a link to this video, and then a link to the blog where you can read about the mission and what's going on for status. All right, so just so after you have Visual Studio Code installed, this is kind of what it would look like. I'll do a quick demo of this, but this is just for reference. The first thing you need to do is enable after you've installed Python itself too, you have to enable the Python extension in Visual Studio Code. So you go down to this little gear icon, push that, then select extensions, and then you'll have to search into here, just type in Python, look for the one that just is plain Python. It'll install the other items it needs automatically. Then once you select it, it'll show up over here into a new tab, and there'll be a button that says install, and you can just tap on that. Since I've already installed it, it gives me different options here in the screenshot. All right, and then the next thing you'll have to do is you can open up the script and run it, but you'll have to install the very first time only, you'll have to install a couple extra additional Python libraries that are used by the script. So as I mentioned, you need to download and unzip the script from my website. And then once it's in a folder, you can go to the Visual Studio. So you can hit the little kind of this little stack of papers icon, and then you can say select open folder, and then just navigate to that folder itself. And then from there, actually you go to file first, the file, open, folder, and then you open that slot. And then there should be a list of all of the files in that folder itself. And if not, you can tap on this. This is where you tap on this icon, and it'll show all of the files. From there, you can double click on this one that says Artemis_2_ground observations.py. That's the main script. And once you double click on that, it should show up as a tab in the main editor over here. And then we also want the terminal to be at the bottom so you can see some of the results. And to do that, sometimes it's hidden initially, but you can click on this little icon that shows like the bottom portion of the screen. If you click on that, this bottom part here will turn on and off, and then you can click on this terminal section here. And then the first thing you do when you click on that terminal section is copy and paste or enter these 4 commands. So it's pip3 space install space skyfield, and then you hit enter. and that will run the pip3, which is the Python package installer. It'll run that and install that package, and you can repeat it with the other ones. One of these may actually be installed by the other ones automatically. It'll just tell you that it's already installed, so you can keep going. So make sure all 4 of those are installed the first time. That's the only time you have to do it. After that, it should run just fine. And then when you're ready to run it, then you can click this button, this like a little play button here, and it'll execute the script. But before you do that, make sure we'll customize it for your location, and we'll do a demo of that here next. All right, so yep, I'm going to do a demo of that. So I'm going to get out a PowerPoint. We'll kind of run through a couple things. All right, so moving this out of the way, bringing over Visual Studio Code here. The first thing is, here is the script that I've downloaded. So I'm just going to double click it here for Mac, and then here it unzips it into this folder. So in this folder, there are 2 files. This is the trajectory data itself, .asc. This is the test one. And this is the Python script. And then there's 2 subfolders, one for Celestia, so it has a couple files that are pre-generated just by me running the demo before. This is the both of these files then have to be copied into the Celestia script folder, and the same with Stellarium. These are the 3 files that will eventually, when you run the script, it'll update these files, which have to be, so every time you rerun it with the different parameters, you have to recopy all of these files into the different locations so they're updated properly. All right, so then in Visual Studio Code, like I mentioned for the extensions, you can click on this little gear, hit extensions, and then as up here is where, these are the ones I have already installed, but normally it'll just show the list, and you can just type in Python, and then you find the one that says Python, and then you'll hit install right here, and then it'll install that. You may have to reboot the application or close it and restart it. I don't remember, but if so, you can just close it and open it again. All right, and then after that, go to File, Open Folder, and this is where you want to navigate to the zip file you have here. So I'm just going to go to Artemis II tracking, and then I'm just going to open it right here. So I just want to open this whole folder, and this is where if you click on this icon here, this Explorer, it'll show all the things. And if this isn't showing up, I think you can also click this icon over here, and that will toggle this extra pane to show up when you click on these. Let me see if I can make this a little bigger. And then we also notice we don't have the terminal down here, so I'm going to click on this icon right here, and it'll show. If you notice, I'll just click it again and on and off. Then you can click on these other things, and then there you get your terminal. So this is where you will want to first double click on this Python script right here, this Artemis II ground. So when you double click that, it'll open the file. So all this green are comments. They're just there for extra notes. And at the top, you can see the library dependencies. So these are the libraries that are needed. So you can actually just copy and paste this. You can say like copy. So I'll just copy that. And then you can paste it right into the terminal. And then just hit enter and it'll run it. And since I already had it installed, it was really fast. But then you can just repeat that for all of them. You can just see some other notes I have in here. Here's the notes on how to use it with Stellarium, how to copy the files, where to copy to, how to use it with Celestia and things like that. And let's see if we can get rid of this little pane over here. All right, so once you scroll down a little bit farther, you'll see this section that says customizable data. This is where you need to edit it to make sure it matches for your location and your setup. So the first one is the Orion trajectory file, the OEM file. So here's where in between these quotes, you need to put the name of the file. So right now it's set up properly for the test data, but as you download new files, you'll need to put them into the same location here. You can delete the old one to be safe, because then it'll give you an error if it runs and it can't find it. But then put the new one there, and then just change the name of that file to match. Then you give your location a name. So when it plots, it shows the right location. Enter your latitude and longitude. Be sure to use negatives for west and south, and use decimal formats. Here, you can look those up on Google, usually if you are unsure of your current latitude or longitude. And this is your elevation above sea level, which you can just also to Google. It doesn't have to be exact, just fairly close is good enough. And then after that, you can specify some of your equipment. So this is where you would put your telescope focal length. So I have it set up with an 8-inch Schmidt Cassegrain with a 0.7 reducer right now. And then your camera pixel size, so just assuming square pixels. Put this in micrometers. Then after that, here's just some options for some of the displays. You feel free to change if you prefer UTC times versus local times. If you really want the Julian date or to show the mission elapsed time from that file itself, it'll show those as well. That way you can help find it on the plots too. And then this is just the output to the file names. I would just recommend leaving these the same because if you do change these, you have to change some of the other files to match. But it's there in case you want to change it. And here's the constraints. So here's roughly the size of Orion. Have set at 19 meters. Looking at the solar ray span. This is the pixels, how big it has to be, a number of pixels before you can see it. That's a constraint. Talk about that in a bit. But I have just a default guess value there. And then this is how high above the horizon you're going to be constrained to. So I have that 15 degrees. And then this is at what point it's considered dark. And this is set up to be minus 12 degrees below the horizon. And that's equal to the astronomical twilight. Astronomical twilight. Oh, I have that wrong there in the comments. And then just some other, so anything above here is basically what you want to configure. These ones you can all leave the same unless you want to change some of the constraints, and then just set up mainly the ephemeris name, your location, and your telescope. And with that, you should be able to run it. Okay, so I'm going to run it here. Everything is set up. We'll hit the little run button up here. The very first time it runs, it also has to download an ephemeris file that has all of the data where the moon, the earth, and the sun, and other planets are. So it's about 100 megabytes of a file, and that'll download it to the same directory that you have your other files. Here you can see it's in progress here. So that just happens the first time, and it takes a little bit. But after that, the file is already there, and then it runs a lot faster. So we'll wait for my internet speed here to finish. And as soon as it downloads, the script will continue automatically. All right, so there it goes. Okay, so I'm going to just resize this part here so we can check out what it output. So it outputs a lot of the assumptions up front. Therefore, if you copy and paste this, you can kind of keep track of different options you tested. And then it looked for the viewing size constraint. It looks through those and it finds the opportunities when the viewing size constraints are met. It even gives you a max for when it gets the largest in this section. Then it looks at the elevation constraints. So this is when it's above the horizon. So this basically goes with the night and day cycle mostly. And then it shows the lighting constraints when both Orion is lit and your location is dark. So it spits out all of those times. And then it looks across for when all of them are met. And that's that final. And this is probably the most important, when all constraints are met. And then it shows the feasible times that will work. And this again is 1. It matches the same I talked about earlier. And it tells you the time. And therefore you can use that to then start Stellarium. Okay, so I'll quickly do just the Stellarium so you can see the rest of the process. So, okay, so now we've run the script. And with that, I'll get this out of the way. Oh, here are the plots. So this is Usually they're pretty small, so you got to make them bigger. It also has an extra plot that shows you distance over time. Put that out of the way too. I'll just leave it over here for now. Okay, so this is where you can use this interactive zoom. So if you click on that, you can zoom into different areas and it'll zoom all of the plots at one time. So if you're really interested maybe in this spot where it gets really large, you can zoom in here. And then you can then notice it's actually above the horizon here, but this is where it is. And actually the Orion isn't sunlit. It's just unfortunately also sunlit at this location. So I would then you can just hit home and it'll zoom back out. You can zoom into different parts. So I think this is pretty handy to look at other options. All right, so after running the script, it also updates all of these files. So I'll just go through the Stellarium ones because that's what I want to look at first. So here we need to copy these 3 files. So I'm going to highlight them all and then right click on them and just go copy. And then I'll have to open up where Stellarium is. So for Macs, I'll show you where that is. For Windows, it's that C program files, Stellarium, whatever I referenced earlier. So here it's applications for me. And then I have a special astronomy one. And then for Macs, this is the tricky part is you have to right click on Stellarium itself and say, show package contents, and that drills down into there, and then you can go contents, resources, and then scripts. And then into this folder, you can just paste those files. Let's see. Paste 3 items. So here it says, do you want me to overwrite them? Because I have already copied them there once. That's fine. I can replace these. You can just hit apply to all. Replace. So it copied all 3 of those files to this location. All right, so now we'll start up Stellarium itself. So here is Stellarium. This is where you can, if you hit this button here, so you open up Stellarium, it'll be probably some different time and date and time. Hit this the second to bottom light. You might have to go to the edge before this pops up. I have them just stuck so they're always open. If you hit date and time window, you can adjust the date and time. So we'll pick a time during one of those script predictions. So this is again the 2nd at 2:38 in the morning here local time. I also have already set up telescopes that I have that you can show the field of view. So I'm going to use this camera and this telescope, and then it'll show automatically the field of view in the sky. I also have a custom, as I mentioned, landscape so I can see where like the neighbor's house and our garage gets blocks the view. All right, so then you can use that to see where Artemis II is now. If right now I think I have already the script running since it was in the background, but what you would need to do is open the configuration window. That's why Artemis II is there. You might not see it initially, so you hit this configuration window. It'll open up to main. Click on the scripts tab, and then just scroll down until you see the one that says Orion, Artemis II, Stellarium. Click on that. So I'm going to stop it since it's already running, but then you just hit this play button and it'll close this window when you start playing it, and then it'll just loop in indefinitely until you can actually come back here and stop it in the future if you're done, or just close the application. So we'll start the application, and what it does is just it looks for when you change the time. So if you change the time, then it updates the position of the Artemis II dot there, which is Orion. So here again, you can see if I go like change it by an hour, then you can see that kind of that jump. That's what the script is doing. So if you double click say like a star that's nearby it, it'll center and keep it fixed, your view on it. And then if you change the time by minutes, you can see, oops, I'm going the wrong way. Actually, I'm going the correct way. You can see how Orion moves. So you'll have to probably pick a spot, say to target a time. That's a time and a location to aim, and then start your long exposure ahead of time. And then as the time goes on, oh, I did pick the wrong direction. Okay, well, that's why you have to play with this, and then you can get familiar with how to plan with this ahead of time. So I'll maybe center on this location. Okay, so I'll center on this. Say I'll center on this star, and then I'll say, hey, I'm going to start imaging at 2:39, and I'll run for 3 or 4 minutes, and it'll just this will simulate what will happen. Well, I guess maybe I'll start imaging at 2:42. Oh, actually, now that I see it's just entering the frame, so maybe start at 2:44, and then set it up for 4 or 5 minutes, and you can then maybe take two in a row, and you can see across that time span where the spacecraft moves. So that way you can try to get your framing that's perpendicular to the path. That way, in case there's errors across the way, you'll get the streak somewhere. Well, I'm sure you know how to plan your imaging for your setup better than me, but this allows you to know where the spacecraft will be at what time in your sky. So that should hopefully be pretty helpful. All right, so that's the demo. I'll go back to the presentation here real quick. The rest of it. I think we covered all of those. So just the process during the mission, kind of repeat. First is watch the launch, so know when it actually launches. Then within a couple hours, get the updated trajectory file, either from NASA's website directly, or I'll link it also from my website. Rerun the script, update the script for the new file, rerun it. Use Stellarium and the outputs of the script to identify good times for imaging. So after you run the script, you have to copy the new files to Stellarium. Just make sure you do that. And then once you have a plan, go out and take some images and then share with the rest of us. So that's really the main steps. I hope this helped. That really is what I wanted to cover. But I do have a few other thoughts in case people are interested in, and that is some of the constraints that I have listed in the script. So feel free to change some of those. So like if you have a clear horizon around you, you can lower that altitude constraint, maybe down to 10 degrees or things like that. That should open up more imaging time. If you think you can image when it's not quite as dark, you can change that angle at which the sun is below the horizon, at which you consider dark. Then there's also one more that I'm not quite sure what value to use, and this is where I had to do a little bit of sleuthing to come up with an estimate, and that is the minimum pixels to see the object. So if right now I have it as 0.1, and I'll show you how I got that, but this is just a measure to see like how sensitive your setup is to be able to detect Orion. So I'll show you how I came up with that value, just to help if somebody wants to change this value or thinks it might be wrong. So I was at first I had thought maybe you had to be a couple pixels wide to see it, but it turns out to not be the case. And I'll just really fast go through how I came up with that. The main thing is I did a couple tests, so I went back and looked through some of my images where satellites appeared, and then I wanted to say, hey, how big and how far away was that satellite to figure out how many pixels it theoretically was covering. And so that's what I did here. So I used the 8-inch Schmidt Cassegrain with a 0.7 reducer for this setup. So here's the focal length, 1,420 millimeters at f7. So with that, I found an image of the Running Man Nebula that I had quite a bit of satellite trails in. So I found one in particular. You can see this is the full image that goes clearly through that. Hopefully that shows up on the recording. And then I went into Stellarium, and because it wasn't that long since I took that photo, and looked for the satellite that ran through the image right in that location. I was able to figure out which one it was, or have a pretty good idea which one it was. So then I Google searched that satellite specifically and found that it was this satellite, this broadcast satellite SES-14, and was able to come up with how big it was, and roughly, and it's in geostationary orbit, so I knew how far away that was as well. So with that information, I was able to calculate. Here's kind of showing my work, how big of it is. So it actually filled up about 0.17 arc seconds in the sky, given that it was 30 meters in size and was 35,786 kilometers away. So given that, and then going through the how many arc seconds per pixel calculation, therefore this setup can detect 0.55 arc seconds per pixel. And since I could see that satellite and it was only taking up 0.17 arc seconds, that means this satellite was really only taking up 0.3 pixels. So if we with a long exposure, we can definitely pick up satellites that are less than 1 pixel in size. So that's where I got 0.3, and then I tried again. I did a little bit different setup, so I put the Hyperstar on the telescope, which brought the focal length down to 390 millimeters, but at f1.9. Same camera, same general telescope. With that, you can see these fainter satellite trails, kind of in that same area. They're much fainter, but they're there in a much wider field of view. So if there are errors, it will definitely capture that. Okay, this is just a zoomed in version. You can definitely see the satellite trails. So I went and found for this time, I went to Stellarium, did the same thing, figured out which satellite it was. Did the same thing, looked up roughly how big it was. This one was a little bit trickier. I had to find like a similar satellite. But with that size, I did the exact same calculations. What's the arc size in the sky, and then figure out how many pixels it would really be covering. So with the Hyperstar and the camera, it really was almost 2 arc seconds per pixel, and the satellite itself should have been 0.23 arc seconds. So that means that we were able to pick up about 0.12 pixels in size, and it still show up, even though it's with a 1 minute exposure. So that's how I set the 0.1 limit as being able to see a spacecraft. So this will also depend on how much light is reflected and things like that, but that's how I came up with that value. So you may want to play with that number. It does significantly change the amount of opportunities you have for imaging, because Orion gets, as it gets farther away, which it gets farther away pretty quick, this gets really small. So if I think I have a more sensitive setup, you might be able to image longer, and that would give you a larger amount of time between liftoff and when you can image too, which has its advantages. All right, with that, hope it helps, and if you get any good images, let me know. Thanks.